Okay. So now we are going to discuss the fourth period, that is reaction power control requirements in a steady state condition. We have previous classes we have discussed how to convert, that is how we can able to convert the converters and all that. Okay. So in all the functions, as I said before, that is in the grade switch. The other side is rectifier and the one side is inverter. This is how the conversion takes place based on the average DC output voltage. We have seen all that. Okay. So based on that, as I said before, there will be some change in current and voltage and with its ratios. Okay. So it happens when it happens means what happening there means there is a reactive power is there. Okay. So we have to control that reactive power. You all know that it is required power is our real power. Okay. So that reactive power, if it exists, means what happens means our power factor will get varied. So if our power factor varies, means what happens? There will be increase in some losses. Okay. So in order to reduce that, what we are going to do is we are going to compensate that reactive power with some reactive power sources in the bus voltage side. Okay. So by that technique, what we are going to do, we have to learn first what is that control strategies we are going to use in order to reduce that reactive power. Okay. So for that purpose, we all know that in a HVDC power station, what we have used there in the initial first unit we have discussed that is a line commutator. That we have discussed it, right? That is LCC, line commutator converter. And after that, we have discussed about voltage converter and all that. Okay. So in the HVDC power station, what we are using, that is a line commutator system. Okay, and that is in a line commutator system, you all know what is happening there. There is a phase difference between this current that is initiating in the valve side. There, what is there inside the converter bridge circuit? That is valve, which is your switching devices. Okay, that is said to be valve. Okay. That switching devices, in your giving some input towards it, and based on the firing angle, what's happening, the operation continues, and we all know which mode of switches will contain. Okay, during the first mode, the switches I have given you the download code. That is in the first mode. What happening? The switch 2 and 3 starts connecting. Okay, based on that, for a 6 pulse converter we have discussed, 12 pulse converter we have discussed. Okay, so with that in mind, so we know that it is current initiating in the valve. What is happening now? The current is initiated in the SCR that is present in your bridge circuit. Okay, that is getting delayed. Okay, that is we are going to support. Why this delay means there is some delay angle in your gate pulse. Okay, so we are discussing that is the delay angle may be either 15 degree or 30 degree, and we have derived all that. That is 15 degree, we have derived 30 degree or 60 degree. Okay, so this current is initiating, the current which is initiating in this SCR, it's getting delayed. With respect to whom it can delay? With respect to the voltage source we are giving as an input to the switching, that is valve. Okay, so that is delayed with the zero crossing over the bus voltage. Okay, so at that time, if this delay happening with this current that is initiating in the valve with respect to the zero crossing voltage means what is happening? There is a lag in power factor. Okay, what should be your power factor? It should be 1. Okay, if it decreases means if it is 0.8 means what is going to happen? If it is 0.8 means what is going to happen? We will in the end. Okay, so if it decreases, if it lag in power factor will lead you to get some losses in the losses in the conversion stage. Okay, so in order to reduce the losses, what we have to do? We have to improve our power factor, or we have to increase our power factor to the sustained value. Okay, so for that purpose, what we are going to do means we are going to compensate the reactive power source. Okay, so I am going to compensate. There is a lagging reactive, there is a unwanted power, that is reactive power, and we no need of that. So I am going to compensate it. So we can compensate it with it. What is the unit for reactive power? VAR. Okay, volt ampere reactive power. VAR. We can able to compensate with, you have heard that name, that is static VAR compensator. Right? So in order to get a steady state response, I am going to compensate using a static VAR compensator. Now I have to connect it in some stage. Okay. Where I am going to connect that means I am going to just connect that static VAR compensator or some other source of reactive power source at the converter bus. For what? For getting a better voltage source. If my voltage source is better, means what happens? The current that is initiating in the valve I can able to compensate it, right? So I can reduce the losses. So for that purpose, what three control strategies available? Which means the initial is conventional control strategies. The next thing is alternate control strategy, and that we all know that is forced commutation method, or else you can note it as this forced commutation method. That is actually station is line commutation only. If it is not commutated properly, okay. As I said before, if in mode 1, switch 2 and 3 is in the conduction state. Okay. Due to some delay angle or due to some extinction angle, what is happening? It's still the SCR is in conduction state. So what is happening? My load is getting increased. So at that time, what we have to be able to do? I can be able to commutate my switches which is present in the bridge by forced commutation method, by using some external commutation circuit to the SCRs that is present in the bridge in the converter. Okay, so that is the third. So now that is the first conventional control strategies method. Okay, so here for our convenience, we have taken the value of the power unit system. Okay, in per unit system. Okay, so that is and we have derived that average DC output voltage VD. Okay, in the converter, the unit 1, you have derived that VD is equal to 3 root 2 by 5 voltage source V. Okay, that is which we have derived in the first unit, that is average DC output voltage for the converter circuit. Okay, that is our output VD is equal to 3 root 2 by 5 voltage source V. Okay, so in comparison to that, I am going to take it as a base converter. Okay, a base converter, that is VDP, which means a base converter voltage. Okay, that is VDP is equal to 3 root 2 by 5 VN. Where VN is here the source voltage, and here what is our source? That is our rated line to line voltage, which is present in the, which is given to the valve voltage. Okay, which is our valve voltage. Okay, and now for next, this is the voltage per unit system. Okay, and then for the base current, that is base DC current, IDP will be equal to your ID is your which is your ID, that is your average DC current. Okay, VD is your average DC voltage which we have derived previously, that is VD is equal to 3 root 2 by 5 V, that is our voltage source. Here it is, we are comparing it with the control strategies. So this we have taken it as base converter. This VDB is equal to 3 root 2 by 5 VN. VN is our rated line voltage. And next our current, that is ID is equal to IDN. Here IDN is our rated DC current. Okay. And now the power. Now voltage is there, current is there. Now what is the power will be? The power base power will be NP into, that is we all know that P equal to B into I. And the PDB, that is base power, since it is base power, PDB is equal to NP into BDB into IDB. Okay, so where the base AC voltage, that is equal to what? That is VB is our line voltage. Okay, and now the base AC power will be what? Will be equal to the base DC power, and that is taken as root 80 by pi times the VN IDB into NB. So now that is base power, that is equal to P power equal to P into I. Okay, here NB we have to multiply, that NB is our number of that bus which is connected in series. Okay, number of connections converted n number of. Okay, so this n base to the VDB into ID. That is our power. And the base AC voltage, that is VB, base voltage will be equal to the line voltage, that is VN, which is your rated. Sorry, here it is. So VN, that is your rated line to line voltage. Okay, and now the base AC power, that is in converter, the left side there is a AC source, and in the right hand side it is a DC source. Okay, that is based on our average DC voltage, or else based on the polarity of the DC voltage. What is happening? The converter operation takes place. That is not the either it should be acting as a rectifier or as a inverter. Okay, so based on that, what we are saying that the base AC power that will be equal to what? The base DC power. Then only our converter will be an effective converter. What we are giving, if it is a rectifier, means it should convert what we are giving as a AC to, it should convert the output to the required DC output. If it is an inverter, means what we are giving as a DC, that base DC voltage that should be converted to as a base AC output. Likewise, the base AC power that will be equal to what? The base DC power, which is 18 by 5 times the your power value. This is the general power value, that is MV into VDB IDB. Okay. So when we are going for the reactive power control strategies, what we are attaining is root 18 by 5 times our PD, that is PDB. Okay. So if we can able to compensate in that range, we can able to control the reactive power. Okay, and by that, now go for the average DC output voltage. What it will be is the change in VD. Okay, in initial stage, when there is no any reactive power compensator, it is set to the average DC voltage, that is VD. And now what we have given to the converter side bus voltage, bus side, we have connected a reactive power source. Okay, in order to control that. Okay, based on the control strategies. Now, at that time, what we are attaining, our power is root 18 by 5 times our original operation, normal operation condition. Okay, and it is how it is that how it is compensated. Okay, and likewise, our VD dash, that is DC output after the reactive power control strategy is included to the circuit. Okay, that is VD the bar is equal to V bar cos alpha minus, and this equations that we have derived the basic operation conditions, that is VD average DC output voltage is equal to what? V cos alpha minus RC into ID. That is RC is what? For resistance that you have discussed already, right? That is RC into ID. Okay, so what is the relationship between RC and XC? So it is what it is XC, that is RC will be 2 times the RC. Okay, and from that I am taking that RC is equal to XC. That is a leakage reactance. Okay, and we have know that due to the leakage reactance also, what is happening in the converter? The change in modes is happening. That is the SCR is not turning off. So what we are going, what we have done? We have gone for the combination systems, or else we have studied multiple mode systems, right? And likewise, the leakage reactance is also one of the factor for the average DC voltage. This is a basic converter voltage. We have discussed the first unit, that is P is equal to V cos alpha minus RC into ID, and by that here I have added also reactive power control strategies, and so I made noting it as VD bar. That is VD bar is equal to V bar cos alpha minus RC bar into ID. Okay, and by that here I am taking V bar as common outside. So here is a term V bar. So when I am taking it outside, here it remains the cos alpha minus, here it is not V bar there. So I have to divide over by V bar. That is RC ID bar divided by V bar. Okay, now this is my average DC voltage when there is a reactive power control circuit is there. Okay, and now the test I am giving that V bar over the denominator. That is VD bar by V bar equal to what? Cos alpha minus RC bar ID bar by V bar. Okay, and now by that what we are saying that the average DC voltage will be equal to what? The basic operation being average DC voltage, that is VD divided by our base converter voltage VDB. What is our base converter voltage? VDB is equal to what? VDB is equal to 3 into root 2 by pi BN. That is this is our base voltage, base converter voltage. That is VDB is equal to 3 root 2 by pi BN. The relationship whenever a reactor control system is implemented in our basic modeling of a converter, what is happening? The average DC voltage we have to divide it with the base converter voltage, that is VDB. Okay. So after likewise, the current response how it will be mixed. ID will be equal to ID by IDB. That is our base current side of the converter. Okay. And next, V bar will be equal to the change in voltage. How it will be? It will be the source voltage V to the base voltage VB. Okay. And we know the relation between the leakage reactance and the resistance. That is, leakage reactance will be the twice the resistance. Okay. So likewise, then RC will be equal to what? XC by 2. Here how much of leakage reactance there? How much of reactance is getting leakage there? XC by 2. Okay, and by that, what is our power factor? Okay, that is our cos phi will be equal to average DC, that is VD divided by VD naught. That is our output side voltage. When it is converted, whenever giving the circuit, there is a different, it is getting converted, and that is whatever VD naught. Here is what your bridge. Okay, so that is cos phi is equal to VD by VD naught. That is equal to what? VD. We can able to substitute. That is, we know the VD value, right? So by that we can get the VD bar by V. Okay. So we can take this VD bar by V, right? What is our VD bar by V? We have calculated. VD bar by V is equal to cos alpha minus RC ID by delta. So what is our cos phi then? Cos phi is equal to what? Cos alpha minus RC ID by delta. So the power factor cos phi is depends on what? The power factor cos phi depends on cos alpha. That is based on the phi angle alpha. Cos alpha minus RC. That is our leakage 1 by 2 times the leakage reactance and our average DC change during the reactive power control system, and in the change of voltage. Change in voltage is source voltage to the base voltage. Okay, so based on this, what is our power? Real power, that is P into P bar ID cos phi. We know that P is equal to PA cos phi. Whenever power factor comes under root, P equal to PA cos phi. And for a reactive power, this P bar is equal to V bar ID bar sin phi. So this reactive power only we are going to this power only we have to compensate. Okay, and here I have told you that alpha, right? That cos alpha, that alpha can be replaced by gamma. If I replace it with gamma means even it can be alpha, but I replace it with alpha means in the inverter side, what we have discussed in the rectifier side, by changing what we can able to attain with the operation condition, and in the inverter side, by changing what we can able to attain the operation
alpha equal to.
In the inverter side, rectifier side, okay, in the inverter side, what is happening? By the extinction angle control, we have seen one technique, right? By the extinction angle control, can you all remember that? By the extinction angle control, that is gamma. We have discussed it, right? That is by extinction, minimum of extinction angle control, we can able to convert with the inverter side, we can able to control it. So I am going to replace that alpha with the gamma. Okay. So for a dynamical value, I am going to give this our prediction. That is alpha is equal to, if I am considering it as 15 degree. At a time, what is the leakage reactance means it is 0.2 per unit. Okay, and the change in voltage is 1.0 per unit. Okay, flows like this means if alpha is 15 degree, xc bar is equal to 0.2 and v bar is 1 means what is our graph response will be variations of Q reactive power with respect to real power. It will be like if the alpha is 15 degree. Okay, so our response will be here to here is a point 1. That is 1.0 per unit. If this extinction angle increases, what is happening? The value of the real power that is getting decreases. Okay, it should not happen actually. Okay, so what is happening means if the alpha value is getting increases means okay. So like if the source voltage can get increases. If the voltage get increases means we can be able to reduce the current. What we can do? We can able to reduce the phase difference, that is currents initiating in the valve to the voltage that is across the zero crossing area. If the ratio is getting reduced means the losses can be reduced. Okay. So under this operating condition, when alpha is 15 degree, x is our 0.2 means and v is 1.0 means what is our power factor? If we substitute these values over our cos phi. Okay, so what is cos phi? That is cos alpha. Alpha is what? 15 degree. Okay, RC response what? XC by 2. That is XC we know that 0.2 by 2. And ID is the current that we can able to get from the overall operation ID current. Okay, and by that V bar value what? 1.0. Okay, if we substitute over here means what I am getting means cos phi that is cos phi that is power factor. Okay, power factor cos phi will be the value of what we can attain means power factor cos phi is equal to 0.866. Okay, if the delay angle I am going to increase, okay, I am going to increase just on 3 degree. Okay, if I am going to increase it by for 15 degree, the answer is like 0.866. If I am going to increase it to 18 degree, then what will happen means our power factor will become 0.851. Okay, so what is happening? The power factor is getting reduced. So if the power factor is getting reduced, that is it should be the voltage should be in 1.0 per unit. Then what happens? The voltage will reduce to 0.9 per unit. If I am saying that if it is reduces means what happens means see. So this voltage should be in 0.1 per unit. It reduces to okay. It reduces to 0.9 per unit. If this one even it is a 0.1 changes in per unit of value, right? So this one unit of change, 0.1 unit of changes will make your current to increase. Okay, your current to increase up to 15%. Okay, we can say it as this voltage source value as 0.1 times or else the change in how much of percentage it is changing? 10%, right? Just a change of 10% in voltage will give you increase the current of 15%. So by that your losses will what happens means your losses in the converter side will be like 30%. Okay, so if this ratio, the change in voltage is 10%, and what is happening? Current is getting increased by 15%, and what's happening finally? The losses is double the time of the current increasing, that is 30%. So in order to compensate all these things, we have to compensate this reactive power QD. What is the value for QD? QD is equal to PID sin phi. If we get able to compensate by using a static PO compensator, that we will be studying later. SVC, StatCom and all that. Okay. By connecting to that converter reverse voltage side circuit, we can able to compensate the reactive power using the reactive power source. Okay. So by that we can able to attain our basic operations of the converter with the reduced losses.